is the most energy intensive process in the mineral processing value chain, and
Oh.
a lot of energy goes into.
Hello, doctor. Hello, doctor. Good morning.
I can hear you, sir.
Can you reshare your slide, sir?
I'm doing that currently. Hmm. How about now? Can you see my slide?
Yeah, reshare it, sir.
Oh, okay.
Yeah, presentation mode. Awesome.
Okay. Thank you. So I chose combination because I believe it's more energy intensive and is the most energy intensive process in the mineral processing value chain. And we are working on reducing the energy usage in that space. And every improvement in efficiency translates to millions of dollars for big mining company. I know uh, Nigeria is not so big in mining like other countries, but at the same time, the little we do, I think we can improve on it. And if we improve on the processing, then we can sell finished products and add value uh, as against what we're doing at the moment, which has its own disadvantages. So I'm looking at exploring efficient and sustainable practices in mineral extraction. Uh, we're looking at combination and energy auditing and how both can lead to affordable and eco-friendly mineral processing. So now, when we talk about comminution, it's just a fancy word for milling and breaking of rock. So, like I said, it's energy intensive. It accounts for 50 to 70% of mine's total energy consumption, according to USGS in 2023. So, the process involves different stages. So we have we call primary, secondary, and tertiary stages of combination. So which are just breaking of particles in the primary stage means crushing at coarse size. I'm not sure you can hear me. There is a background noise. Okay. Okay. So there are different stages. You know this already. Primary, secondary, and tertiary stages with decreasing particle size targets. So for the primary stage, when you have your mineral comes in long, big lumps, and you have to do primary crushing using any type of crusher, either jaw crusher, cone crusher, gyratory crusher, or just to break the particle down to a level that will be processed further down the value chain. Then you have to continue to the secondary stage, depending on the mineral of interest. You keep breaking until you get the desired size fraction where you will liberty of mineral. So this process is very energy intensive, especially when you are dealing with decline or grade. So, for instance, copper grade globally is declining, and more energy is required to extract copper from lean ore bodies. So, the more the grade declines, the more energy is required. This may not really apply to us directly in Nigeria. Maybe the grades of minerals we process are still very good, and uh, we even the artisanal miners, uh, they have their own crude process by which they could get this concentrates out. So, but globally, uh, we have this energy issue. Um, so, well, you already know this, that, but I just put this one in order to say that, okay, combination plays uh, an important role here. Before we separate, sometimes we have to grind and regrind uh, before we get achieve the desired size fraction. And the other processes also uh, consume energy, but not as much as breaking and milling of particles. So the systems that we have now, which are the equipment used globally, are grossly inefficient. And because they are inefficient, so about 40% or less of the energy output actually goes to useful work in comminution. So when you have a process that's it's 40% efficient, then you want to do everything to optimize the system. If you optimize the system, then it translates to profit uh, for the miners, and at the same time, it's going to affect the value of uh, the product. So that's why we're looking at this. And energy demand in mineral extraction, globally, about 2% of global electricity goes into mining. And well, this is not like a fair assessment because this 2% is not coming from all the countries. So we know that in Africa we have energy problem, um, especially in Nigeria, which is supposed to be the leader in energy production in Africa. But for some reasons, we are still struggling to achieve that. Uh, South Africa used to supply or used to generate about half of what sub-Saharan Africa generates in electricity, but currently South Africa too is struggling. And if you look at it, there is a relationship between energy production and development. So that's why the countries that produce more energy, they are more developed. So there is a direct relationship. If you plot the graph of energy production against human development index, you see that it's better for some countries than the other. So what I'm saying here is this. While 2% of global electricity goes into comminution, it may look that, insignificant, but it is if you look at it on a larger scale of process engineering globally. So about 40 kilowatt hour energy per ton for a typical mine site in during processing. Um, so now, because it's a workshop, I will go a bit deeper into explaining breakage because I believe strongly that if we to be efficient in our production, we have to define our own energy consumption and our own interventions. So to reduce the energy production, the energy input for production in Nigeria. So because our own case is, I mean, it is a bit different. Uh, Most people generate their own energy, and the cost of energy, even though it's affected is determined rather by the cost of energy in Nigeria. So when I say energy in that context, I mean like you have to buy diesel to power your own generator and so on. So even though that will be affected by the cost of diesel and other energy uh, uh, products or energy produced in Nigeria. That also depends on the person who is generating energy for mining you have to deal with. So if your system is efficient, what happens is you use less energy. And when you use less energy, it translates to savings for you. Now, and that also will make the cost of production competitive on a global stage. So, if, for instance, let's say copper is sold for $2 uh, per whatever house or whatever, and if your cost of production, you are able to bring it down in terms of energy savings, even though there is a blanket cost, you sell your product, but you use less energy, so you still have some savings. So it doesn't matter how you look at it, you are still saving energy. So now, before we can actually design our own equipment, our own machines, and also our own value chain, we need to understand what is happening, the science of breakage. And people don't waste their time when they do this, when they study this. Some spend their whole life trying to provide necessary interventions to reduce energy consumption in this space. So it's a big deal. Yeah, but we need to understand that before we can embrace uh, going through this physical processes and using science to actually achieve what we want to achieve. There is no way you can do any meaningful or develop any meaningful interventions here without understanding breakage. So I know Dr. David group, they do a lot of work on particle breakage as well, and understanding uh, shear, strain, stresses, and other uh, fracturing of materials. So essentially, properties of solids that influence breakage mechanism. You have the elastic versus plastic, that is the stress-strain relationship. So what is the impact of stress on the particle, and how far does this stress affect the crystal composition of the particle? So if you take a piece of barite, for instance, and you do some loading test on it in order to see how much this material can withstand the stress that you put on it, and when will this material break, and you are able to take some reading, that will tell you how hard this material is. Is it, and also you get information like, is it brittle or ductile? Okay. And if this material is not as hard as uh, you you would require heavy equipment to process, are there other ways you can process this using less energy? So those are the things that we can begin to think about, and this will inform our decision when we do our designing. So the design that I'm talking about here is peculiar to us in Africa and in Nigeria. It's very expensive to import heavy equipment from companies that are producing mining equipment globally. And honestly, the physics, the science that is being employed to producing this equipment are fundamental. So they base on all these tests that we're doing. Now, when you understand this, you can design your own. Fabricating it is not a problem. I know they can do that locally. Fabricate your own machine, especially if you are dealing with modular mining. If it's not like on a very large scale, uh, then even if you import the raw material, you can be able to like assemble your own equipment, and this also will lead to more efficient system and less energy. Well, um, so the microstructural differences in the physical properties of mineral, the adjacent mineral, that is it hard, brittle, or how does this arrangement affect this microstructural properties? So you know that rocks are heterogeneous and you have different composition.
When she's talking like she's paying money. Again,
So
I
these
don't want to see.
arrangements affect breakage because you have different texture of these mineral faces that are bind together by different crystal forces or different molecular forces within the bulk of the material. So yeah, all of these are very, very important. But the good thing is that a lot of model is available out there, both mathematically and also from micro scale to macro scale models, computational models, and other models. Now we're looking at machine learning uh, and other models that have been developed for this. So we may not need to go back into developing our own models. At least that does not apply to the players in the industry. You can leave that to us in the university. But some models have been developed just using this information, and these models are available, and I can explain to you how to use this model. Um, and they are also like um, there are also commercial software that has been developed that use all this information to create a user interface that makes the user interface easier for people to use. But these softwares are very, very expensive, but you can create your own. You can also, if you understand the process, you can use open source and uh, codes that are free to just like develop your own uh, user interface, and you are able to like input the necessary parameters and you get your graphs, and that will inform your decision and so on. So part of the reason we do all this. So now the surface property, which is very, very important. Um, so from fracture mechanics, for an isotropic material, this is a common relationship. And this is just like critical stress to initiate fracture is proportional to surface energy, which depends on the number of floors on a surface. So a lot of people have worked on this, and they were looking at uh, micro parameters to quantify and looking for how best to do this. And different people with different ideas on what to do and so on. Uh, like I said, work is still ongoing, but there are globally accepted parameters that we use to quantify or our breakage and stress analysis. So, for instance, the surface property is very, very important. So that tells you what you do and how uh, your effort is uh, affecting the surface property of the material. So all these parameters are fundamental and can be calculated with this relationship. So I think this is straightforward. Things you can do by hand calculations. You can also do this by modeling. So historically, in combination, different people have worked on this. The model that has been used and the oldest model documented for us was developed by Rettinger in 1867. So as far back as 1867, people have started thinking about ways by which they can calculate breaking or milling of materials. And also, if you know then you can reduce or increase. Uh, you can improve on what you know because you already know it. And the advantage they had, the Western world had, was that they were able to document things early enough. Uh, for us in Africa, I know we are mentioned. So if someone even had developed this earlier than Ritinga in maybe Nigeria uh, or elsewhere in Africa, because it was not documented, so there is no reference to that. So until we learn to tell our own story and document things down, which I'm so passionate about. So, if we are developing equipment in Africa, in Nigeria for mining, and it's working for us, we need to document this. We need to patent this. These are ways to put this uh, out there for other people to see, and people will reference.
We have
So, Oettinger developed a model in 1867, and in his model, energy usage is proportional to the surface area created. So each time there is energy input into material, there is a level of damage that is done to that material. And that damage, the way he measured the damage was to look at it in terms of the new surface area created. So the energy has done something to the particle, and what is it that, how do I measure that? So his own way of measuring that is to use to measure the new surface area of the particle. So he did this at micro level. Now in 1885, Kick tried to improve on that model, and he looked more into the energy production, the energy proportional rather, to reduction ratio. So if there is an impact on a bigger particle or a coarse particle, there will be breakage at some point. And that breakage, now it tries to relate the energy input on the material to the reduction ratio as it occurs in the breakage. So I will explain that. And it's very important for us to understand these models, because if we do, we will understand the current models that are available to quantify energy use in the system as it relates to milling and breaking of material and even classification. So in 1952, so you can see the trend, 1867, 1885, then 1952. Bond now came up with another theory that we call bond theory. Bond theory is very, very important and relevant even to what we do today. So bond theory or bond postulation was successful in a way. So we have energy proportional to the square root, 1 divided by the square root of the ratio of material, which are essentially the feed and the product. So you have what you fed into your system, whatever system you are using to break, even if it's hand that you are using to break the particle, you have an original size, which is your feed. And after you input energy, you have your product. So one is X2, the other one is X1. So, and it looked at the energy proportional to that by this mathematical relationship. Then after that, a lot of things now happened. So there is an industrial revolution that now led, evolution, right, that now led to enhancement of the capability to model. So we started having different computational methods by which we can do large-scale statistical analysis, and we started improving on our ability to explain mathematical relationships. We started looking at differential, like increase differential and partial differential products, integrations, and stuff like that. So all this now enhance our capability to do more. And you know that things have since then. So let us look at rectangle theory. So
Morning, sir.
sorry, I'm
Thank you.
okay. So rectangle surface theory, the mathematical formula is this. So which is essentially, I said, energy.
Because it's don't go wrong, collect it. How is no? I don't know. You know, I say I don't go stop this. I don't know say we don't go collect it.
Dr. David, can you hear me?
You know that you know the collect that.
We are the collect.
You know where they collect that. This I know. That one is similar. This is not everybody like bread like. Bread and fish. You don't have bread and fish. You chop bread from so there you have to stop and go.
Dr. Olivide, can you hear me?
Yes, I can get this question.
You can make me a host so that I can mute them directly, please. This is Ken speaking,
I
please.
will appreciate that. I'm not using my headpiece, so it's a bit loud and it's causing some feedback.
Ah, and the past day, didn't hear my sister.
Okay.
The past day was my wife. Yeah.
Oh, okay. Yeah, sorry about that. So rectangle surface theory, we have mathematical formula, which is energy is proportional. The energy consumed is proportional to the ratio of the product size and the feed size using this relationship. So he was saying in essence that what he was saying in essence is that constant energy per unit of surface area generated. So the new surface area produced by crushing and grinding is directly proportional to the useful work input. And this is still applicable in uh, especially for fine grinding today. I mean, operations below 75 microns. Uh, so it's also like the first theory that we know that is attributed to comminution. So that was the first theory of mechanical or mathematical relationships in comminution. It has its own limitations. This theory neglects energy consumed in elastic deformation before fracture and also does not account for all energy losses in regrinding operation. So it does not account for energy losses. So that's the limitation of this particular model, which is the Rettinger's theory.
Come the way I want it.
Let me see.
Just like what I imagine.
Okay, then let's continue. So after Rettinger's theory, we have the Kick's theory. So we usually call it the volume theory. So it's based on volume reduction principle. So what he was saying in essence is that constant energy per unit mass for similar relative reduction. And this theory is more like using a blanket method, not minding different textural composition of the material. So even though he acknowledged the fact that rocks are heterogeneous, but he still said that, okay, the breakage occurs along floors, so it doesn't really matter the composition of rocks. So it was saying in essence that work required to reduce rock from, let's say, 4 centimeter to 2 centimeter equals work required to reduce rock from 2 centimeter to 1 centimeter. And we know, based on our knowledge now, that this is not really the case. Because, you know, if you are dealing with bigger particles, then you are looking at impact. You want to improve on your impact, the impact energy. So it's just like you have a big particle. I remember when I was in Abuja, so there is there are people who break rocks with their hands. So they just have a big rock and they have hammer and hit it on it and it's going to break. That's impact. So which is what it's applicable in primary crushing. It's just impact. You're using impact to break. But if you are going smaller, then it's difficult to still use impact. Because that would be like killing a fly with sledgehammer. So if you want to go finer, you may need to move to another form of another mechanism of breakage, which may be shearing this time around. So that is why, like when you're milling on the stone, you are applying a kind of shear stress on it. So that's what you are doing. And when you want to use impact, you pound. So, but he was saying in essence, what he was saying is that, oh, it doesn't matter. We just look at it in terms of volume. And the interesting thing is that even though he made this postulation decades ago, I mean, long time ago, we still use this volume method for our analysis till today. Because when we do serious analysis, we do what we call binning method in micro, and when we move it from micro to macro level of analysis, we use binning method. So it's just like you have buckets and you pack your materials inside. You analyze that, you pour it, you pack another one, you analyze and you pour. So then whatever information you got at that micro level, you use it to build a spectrum of what is happening to the whole flow. So essentially, that is what the theory is talking about, and it's still applicable today. However, it has its limitation, like I said. It's optimal for coarse crushing, like I said, because it's based on impact. So anything fine, it's not effective. So Kick's theory has been validated across multiple material types. It effectively predicts energy requirements for large particle reduction, but fails to account for fracture propagation dynamics. So this is what we observe about fixed theory. Then there comes bond theory. Bond theory is still very useful to today. Those of you in the industry, you use what we call bond index. So, and bond indices for different materials are still very relevant to today. So it is more recent, and because it came in 19th century or late 19th century. So, and since then, bond theory has been improved on, but it's still very, very relevant in the mining space or in the mineral processing space. So used in 75% of mineral processing operation, improved accuracy from 30 to 40%, better prediction than previous theory. Then work index concept, this was later introduced for different material. And if you look at the trend in the improvement of this equation, all the equations are still based on Rettinger's postulation. It's just that they keep improving on it based on the graph. So when you plot the graph, you see differences in the graph. I'm not able to show you the graph now. So it's now like how you improve on the slope of the graph. So Bond did very good work, and his theory is still very relevant. So useful work input per ton is inversely proportional to the square root of the new surface area produced, derived empirically. So it's very relevant to the industry. This was derived empirically from operating data and experimental test results. Then, well, like I said, so it's compromise between Rettinger and Kick theories, and it's still used for most mill design. So this is just a summary of the three main models that have been developed over time. And on this, we build our research. So why do we care about research in breakage, comminutions, and stuff like that? Why do we bother ourselves on conducting research? Well, the main objective is reduce unit operation cost, that is dollar per ton. Like I said, if we're able to reduce the operational cost, then we will get, it will translate to more profit. So the other thing is that because the ore bodies are getting very lean, and we need to maximize extraction of our minerals from the gang. So this is really, really important. Gone were the days when we can afford to waste some of the valuables during processing, but now everything can't. In fact, most mining operations globally are scavenging for minerals from their tailing dams. So it's that serious now. And also because of environmental issues, you want to, as much as possible, maximize your recovery and reduce the use of chemicals uh, and also reprocessing. So all of this are what we try to reduce and why we do research. So reduce energy consumption, reduce the use of toxic chemicals, reduce the, the waste you generate, and so on. So you optimize the system essentially. So that's why we do this research. We throughput, results of energy efficiency. Where we have two kinds of breakthrough, we've been able to do some novel technologies, which includes microwave, ultrasonic, and using electric impulse. So retreating material before breakage and so on. Recently, we have been able to do carbonation of mineral. So we have special mill where you first pump CO2 into the rocks, and this will open up the pores, and you can now break. And we realize that breakage is faster after you have weakened the pores. So so it's more like you are breaking you are using less energy because you have caused some internal damages to the pores of the rock. And also that's while you're using lesser energy, that's also like a form of carbon capturing, which is common in the West. So factors affecting fracturing, which you also must know before we proceed. So ability to fracture rocks depends on degree of internal strain, which is influenced by the composition, like I mentioned earlier on, the nature of chemical bonds, the grain boundary, number of internal flaws, number of surface flaws, which will decrease surface energy. So you need to understand all these factors before you know what method to use. And while this may be difficult to get if you do not have the necessary material characterization equipment or mineral characterization equipment, a lot of work has been done in this space for base mineral and also for base metal extraction and so on. So we just need to read a little more. And also that's why universities like AUST and other research institutions in Nigeria uh, are developing capabilities in this space to study the material composition before you begin to break the material, so you know what to do. Because if you are able to do this, you will understand the process of milling better and you take an informed decision. So it's good to understand all this about the material that you're trying to break. Now, the breakage mechanics mechanisms, essentially we have four: impact, I've explained that. Then you have compression, you have abrasion, and you have chipping. So it depends on the material and the size fraction you are dealing with. That will give you the that will help you determine the right or the appropriate breakage mechanism to use. So if you're dealing with coarse, you want impact, and when you're going finer, you will do like abrasion. So you'll be looking at attrition milling and so on. So and different methods, different mathematical modeling for different mechanism. But now we have the capability of bringing all this together during your modeling, and you can, as engineers, do your design on your computer before you launch or your design on the field. So, for instance, impact and compression breakage, particles shatters into fragments with minimal secondary breakage. So it depends on what you want to achieve downstream. Then you have to understand size distribution very well. That is, if I'm able to classify the material properly, even from the time you do your explosions and you look at, okay, how much of damage has been caused to the material, what size fraction am I looking at? There are also models out there. For instance, the Gordon model is good for size distribution equations, and all these are available mathematically. Even you can do all this in Excel to be sure that you have the right size fraction, and you would know if you already have the right department for your process downstream, and you really do not need to mill any further. So we have this relationship in Gordon size equation, where you have cumulative fraction passing of a particular size fraction. Then you have the size modulus, and you have the slope as the natural logarithm of the input size divided by the output size. The impact divided by compression breakage, n equals to 1. So you just need this relationship, and you can use that for your classification. And there are other relationships, so it depends on what works best for you, and we can derive our own at any time. So it's essentially looking at energy input, the size fraction, and classify. So now the reason I'm going systematically is because all these relationships are useful for the big model. So, for instance, the bond work index now, you have your power draw versus product particle size and throughput. The power draw is very, very important. You need to understand the power that you are using to achieve a purpose. So machine can run at their base power, but when you load a machine, it's going to the power draw will increase from the base power because it's using more energy. So you need to understand the power draw. For instance, in milling. So when you load your mill, what's is the power consumption like, and so on. So that is what we can use the bond index for, to understand the power input, the work that is achieved by the power, and until you get the desired milling fraction, and you can quantify the power. So you can quantify the energy used to achieve that. So for instance, bond measured grindability of various ore using a batch mill in closed circuit with a screen. So that's what he did. And for ball mills, he maintained a circulating load of 2.5, and for a rod mill, 1.0. So he conducted parallel tests using like 8 feet diameter ball mill and rod mill. Then he obtained this ratio of a plot of work input versus the FAT minus the PAT. So that's 80% feed size and 80% output product size. So, and it got a straight line graph using this scaling method, that is square root of both of FAT minus PAT. And the proportionality constant is attributed to work index. So the work index was obtained using an empirical evaluation for size reduction in a ball mill. At this point, I want to emphasize the use of the importance of keeping data also, because we're getting gradually to the point where we can use statistical equations to like check your power consumption over time. So if you keep data of your process on site or your processes on site. So he used empirical data and he plotted this graph, and he obtained a straight line graph, meaning that there is a direct correlation between work input and the feed size and the product size using this relationship. So the proportionality constant is the work index. The work index was obtained using an empirical equation, like I said, with this relationship. Then you can calculate your power as the work input multiplied by ton per hour. So you can estimate W, and how to do that. You use geometrical properties of the mill. So measure rod mill and ball mill grindability using the standard procedure. Calculate work index using Bond's empirical equation. Use the work index to calculate the work input. So, and the total power required will now be W multiplied by feed rate. Then you estimate your size of grinding mill using equation relating net power per mill versus mill geometry and operating condition. So we have all these equations, and we can, if you need all this, we can also provide the equations for you. So typical work indices, a lot of experiment has been conducted using this method, and different materials have their work indices. So you have bauxite, so 11, cement clinker, corundum, dolomite, feldspar, granite, and so on. So, and there are material documents that serves as reference. Yeah, I'm sorry, I've not really, I don't know if you want a break, but if you want us to go all the way, we can go till we complete this session. Then if you have questions, and we can discuss. I have few more slides to go, so maybe we should just complete this section. So, for instance, for example, what is the total power required to reduce particle size from F80 equals to 1 millimeter? So the product size, 80% product size of 50 micron for all with work index 15 kilowatts hour per ton at capacity of 2,500 tons per hour. So that's like a practical application of what I just explained to you. And you substitute in the value and you get 1716 kilowatts. So this will allow you to understand while your intervention is working. So if there are interventions, you can calculate to see the difference in power. So now modern theories and approaches. Well, while we are still using the traditional mathematical relationship to do our calculations, because of the improvement in our capabilities. So we are able to do this on a large scale, and we can do this on a computer. All the models out there, if we understand the models, we can easily put this on the computer and check what these models do to our material, and the corresponding power draw, the corresponding the intervention, and these allow us to take informed decisions. So we even have predictive models. So if I'm going to work or I'm designing my plant this way, this is the energy that will be required to produce Y amounts of material. So we can model all this now with our capabilities. The common ones, we have the population balance model, which is a statistical approach to predict size distribution, evolution over time. So using some partial differential equations, and you can easily model this with different codes out there. Even you can do this in Excel if you want to, MATLAB, Python, and you can use hand calculations if you want. So there's discrete element modeling, which simulates individual particle interactions and breakage events. So this will enable you to track what happened between particle and particle, between two particles. So if you have a mill, and mills are like black boxes. You cannot see what is happening, the interaction of particles in real time, but you can model it based on the physics principle of motion and interaction. And using appropriate breakage model, you can tell when there is breakage or not. The other one is machine learning model, which has really improved our capability to predict what happens to your material. So it reduces prediction error by 45%. So compared to classical methods, there is this disparity between your computational results and reality on ground. So people on the field, they actually face they face the problem in real time. So they know, oh, I have to use X amount of energy before I achieve this product size. So sometimes when you compare to the predictive models that we have, using classical methods, you see this disparity. It's close enough, but at the same time, not accurate. But with machine learning models, we can predict accurately, uh, well, very close to perfection, not accurately, but close to a perfect prediction, uh, the relevant intervention. So we can now say that, okay, this is what is going to happen if we go this route. And if we make these interventions, this is what will happen, and so on. So machine learning capability is really, really helping us to improve on our models. So there are also microstructural approaches where you look at your materials from atomistic perspective, and we have this capability as well to study mineral scale properties and defects in breakage predictions and so on and so forth. A few examples of how this works. So this is just a typical example of population balance model where you can use empirical methods to study what is happening in your mill and looking at how materials are breaking over time in the mill. And you look at parameters that is causing this over time. Well, population balance models are good. Some have criticized it, that it's not accurate, but we'll keep doing our best to ensure that we get to a perfect model that will help us to predict the performance of milling equipment. So the discrete element methods, we can model what is happening. The video you are seeing is just particle interaction and also a kind of, we use this interaction to build models to show us in real time the energy in our models. We use that to quantify breakage, and we can extract information from modeling these materials and use this information for our post analysis. And this will give us a better idea of what is happening in our system. So these are improvements and things that and they are not rocket science. These have been built. We just need to know how to apply this, and that is what is important. And well, the industrial applications and energy considerations. So every intervention matters. So portion of mining energy using comminution. If we can reduce this, it's going to be cost effective. I mean, it's going to translate to profit rather. So, for instance, their technology based on all this modeling, we have been able to design technology that improve on the traditional milling systems. And we have HPGR, for instance, and HPGR is nothing but just roller mill that work efficiently in bridging the gap between traditional primary milling and secondary milling. So you can actually break particles into smaller sizes using HPGR. So, and it has proven to be efficient and has reduced comminution energy significantly. So, and these equipments are expensive. but the good thing is that we can produce our own locally. We still have optimization potential, so that is why work is ongoing on reducing energy consumption in this space. So, savings, we also have real-time sensoring and monitoring of particles and so on and so forth. All these are expensive, but they also have the benefits of improving the system. So, future direction, AI will play a major role in the future. The truth is that we're going rapidly, so we're advancing rapidly now globally in our capability to mine uh, minerals. And trust me, uh, it's going to be easier and it's going to get better. And the big boys are really playing actively in this space. So AI, it's will be very, very instrumental to this future that we're desiring. And also data will be very, very important. So sustainability focus, that's also another one, which is really, really important. We know that we cannot do without minerals. None of us can do without minerals. The phone you carry about 66 minerals goes into producing a mobile phone, just one mobile phone. So, and if we talk about sustainability and the premise of our argument is wrong if we are looking at sustainability on the surface, because the mineral, the ore body that we are mining is actually a finite source. So it's depleting. So it's not renewable. And if we're now talking about sustainability in terms of, oh, let us go for more solar power, solar panels, let us go for wind turbine. For instance, one wind turbine, you need a lot of copper, tons of copper. I cannot quantify it offhand now. So produce just one wind turbine. So you're talking about sustainability, and from that perspective, and the source of your sustainable energy is from a finite source. So sustainability, indeed, we have to focus more on sustainable mining. It has to focus more on recycling. It has to focus more on putting less demand on mineral if it's possible. Then that's just the way I see it. So big mining companies are working now to reduce the carbon footprint in mining, and they do this by different methods. Some do a form of carbon tax, some invest in renewable energy, some in efficient equipment, just like we discussed today. So advanced simulation, like cutting design, cutting edge design, that will cost by 25% through virtual testing, enabling rapid prototyping of new comminution equipment. So we just need to design new equipment, and this will come from our design and our models. So holistic optimization, integration with downstream processing for complete systems approach, breaking down operational silos to improve efficiency. So this will be the sustainable pathway and principles of energy auditing. We have looked at all this, but we need to know where we are coming from before we know where we're going. So we need to first see what is the current state of our system. So we need to collect energy consumption data across all operations. This is really, really important. We need to benchmark this against industry standards, global industry standards, to be sure that we're using average energy for our production. Then analysis is very, very important to see which of the system is inefficient, and then that will help us to develop actionable plans for improvement. So best practices, we have looked at mass and energy balance calculations. This is really important. What goes into the mill, what comes out, and the energy required to do that. We also have, we can benchmark this against bond work index. And we look at circuit optimization. We have to redesign in some cases. We have to look at the efficiency of our design and what is happening to our design at every time, because there is wearing and the system, because it's mechanical, it gets inefficient over time. So this is very, very important. Auditing this and checking on this. That is continuous monitoring, implement real-time energy analysis, and tracking systems. So, and this depends on the system you are monitoring. Innovations for efficient and sustainable communication. I've explained that we already have HPGR technology, high performance grinding rolls, reduce energy used by up to 40%. I've also explained that we may need smart control, that is control system, and this work with predictive model. So, and also that's why we have AI tools and sensors to optimize the grinding parameters in real time. Then we have pre-concentration, which reduces volume requiring energy intensive grinding. So there are case studies. We have different companies that are currently doing real-time monitoring and optimizing their system. For instance, the Barrick Gold, they have real-time energy monitoring, and that has given them like savings of up to $5 million because they monitor the energy they use and they also optimize their system. BHP Olympic Dam in Australia, they did circuit optimization. There is a routine for them, and that has helped them 20% throughput gain and 50% in energy reduction. Then they also have renewable energy integration into their systems. This will be my last slide, conclusions and action steps. Cost reduction, lower emission, future-proof operations. Then implementation, we have to install efficient technology, and that is what we have discussed so far. Conduct regular energy auditing, and we have to map out like energy flows, and we have to identify opportunities for optimization, for improvement, for new design, and so on. Well, I'm sorry that it's a long one, and thank you for your time and attention. I tried to make it not too technical and at the same time straightforward. I hope you gain one or two things from my presentation. I appreciate your time. Is there Are there questions? If there are questions, I'm not sure if I need to unmute anyone, or if Mr. Shion can help me with that. So, are there questions? Does anyone have something to say on that? Are there concerns? Are there things you want to ask me? I can answer if I know. So you are welcome to ask me questions. I hope I was communicating. I hope I wasn't talking to myself. Yeah. Okay. Or you can post, better still, you can post your question and I'll do my best to answer your question. Question? Well, okay. Mr. Sean, you are saying something?
Prof, can you hear me, please?
I can hear you.
Okay. Thank you very much for the wonderful presentation. We really appreciate it. Learned a lot. Can you please speak a little into automation, autonomous, in combination with
Oh,
if it's something we can achieve, that is achievable?
sorry. Your voice is echo. Can you come again?
Give me a second.
Better still, you can type. I'm struggling to hear you. Yeah. Okay. You said I should give a summary. Hello? Then I cannot hear you. Hello?
Can you hear me now?
Yes, I can hear you. It's still echoing, but I can hear you.
I was saying if it's
I don't know if others can hear you, but the last thing I heard was I was
okay.
saying.
I'm sure you can hear me now, sir.
Yeah, I can hear you now.
Okay.
Then
I was saying, if possible, if you can speak a little on automation, autonomous system in combination.
automation in combination. Is that your question?
Yes, that's my question, sir.
Oh, okay.
Maybe
Thank you.
something in this sub-Saharan Africa. I know we are a lot behind in terms of technology and all that.
Mm. Well, thank you so much, Mr. Shen. Automation combination, essentially, or mineral processing, refers to the integration of automated technologies into size reduction. So we know that this will significantly enhance efficiency and also
Done for
safety.
today. Great job. Well done.
Thank you. So, which is a good, if for anything, safety, which is very, very important. And in other climes, they have begun to do some very high risky practices in the mining industry with robots. So robotic technology. Well, I wouldn't say that we are still struggling in Africa. As a matter of fact, I think Africa pioneered a lot of invention in the mining space. Last year, I was in South Africa and uh, we were discussing with some mining players, and I noticed they have started robotic mining. They could power some underground heavy equipment from their control room. And when they blast, uh, I had to follow them into the pits and about 3 point, I think it was about 3.5 kilometers into the head crust. They've dug a lot of hole trying to do, they are doing gold mining. So, and I noticed that, okay, that was where I stopped, 3.5 kilometers. But there are still some people further down, so about 5.7, and the condition gets very uh, it's really tough down there. So there are some places you want to send robots to if you really want to do pit mining, and you want to consider the safety of your staff at least. So this also informed their decision to go into robotic mining. Trust me, when anywhere there is valuables, people will go all the way to invent anything to achieve that purpose. So in Africa, there's some level of robotic mining going on. That's the point I'm making. The other thing is, you see, the control system in mineral processing is not rocket science. So it's just like understanding the whole loop. So if you understand the whole loop and you can monitor your system in real time, which can be achieved by a physical system, and you install sensors on that system, or you replicate the system through digital twins, and you have a digital version of your whole system, your plant, your unit operation. You have a virtual uh, replica of the system. You can now use that virtual replica. You can use it to control the physical system, and you get real-time data, a kind of data loop. So you are able to design autonomous or semi-autonomous equipment, like crusher, conveyors, and stuff like that. So all these are very achievable, just using sensors, digital twins, and also autonomous systems for our design. So it still follows the same logic. It's the same logic, and we are already doing that. Especially the big mining companies are doing that. That's the truth. They are investing in automated systems, and I think if we continue like this, I can say that like in the next 10 to 50 years, most mining operations will be conducted by robots. I mean, in some parts of the world. So people will just sit down in the control room and monitor the whole system. So that's just the future. And yeah, in Africa, I think we're already getting there. But in Nigeria, the issue with Nigeria is that we're not so big on mining. At the same time, uh, I think we just need to, especially the players that I'm talking to today, I think we need to design our own system, modular system, efficient system that will be able to achieve the same purpose. So if we depend on all these sophisticated technologies, then it will be very difficult to go on that uh, scale because, and it will be also difficult for us to process, to sell finished goods. We will just extract the mineral and sell at ridiculous prices. That's what we'll continue to do. But if we really want to go into this space, we need to start looking at improving on the technologies that we have locally and create efficient systems. We are not doing so much of pit mining, as far as I know. I think in Nigeria it's more of open surface mining. So, uh, uh, yeah, I think we may not really need to send robots into the pit to go do some things, but at the same time, we can automate our systems and make them more efficient. And all this can be done locally. Students, even polytechnics in Nigeria, would design all the systems. And yeah, I know what I'm talking about. So they will design these systems, and we just need to use what we have to achieve our own, to develop our local production. Yeah. Thank you, Mr. Shion, for that comment. I hope I answer your question. If there are other contributions and questions, is Mr. David, is Dr. David back?
Thank you very much, sir, for the explanation. David is not here.
Okay. So,
Go ahead, sir.
I've been asking other questions or other things you want me to speak to before I go. Yeah. The network is really bad. Barely hear anything from my hand. Yeah. Okay. I will hang around a little and for the moderators to tell me what to do next. But thank you so much. I appreciate this opportunity given to me to present. If you need anything from me, you can reach out to me through Dr. David. He knows where to find me. And I will do my best to respond to you. Thank you. I appreciate your time. And if there are no questions and contributions, then I think my work is done technically, except if Dr. David thinks otherwise. So I will be here. Waiting for him. Yeah. Well, thank you so much for your comments, Mr. Mohammed. I will tidy up the slide and add references where I needed to, and I'll send it to Dr. David. Then you can share it with everyone. That's okay for me. Okay, thank you, Doctor. Doctor in the making, Dr. Shion. So take care, and yeah, I think I can hand over to you. And I think Mr. Adamu has been very quiet today. What's going on? Okay, I think I can hand
Thank you
over
very much.
to you guys. It's now 6:15 a.m. here in the U.S., in Pennsylvania. So I need to go prepare for work. I appreciate the opportunity and thank you so much, everyone. Thank you.
Thank you very much, Prof. On behalf of the team, I want to appreciate your efforts. Thank you for the enlightenment.
It's my
Thank you,
pleasure.
everyone, for participating. We wait a few just